It's a real pleasure to be invited back to Berkeley to speak on this topic. I was a Haas alum back and graduated 19 years ago. And during my time, the library school at the then time was changing to the School of Information. And Hal Varian, who I'm sure you guys know, was the inaugural dean, now obviously the chief economist at Google and professor emeritus of the school. And it was a tremendously exciting time. The web was just starting. Netscape had just got going. And all of a sudden, over the next 20 years, we've been collecting lots and lots and lots of data. The charts have been through the roof as you see them. And I think it's a good time. And I've prepared this talk especially because now I've been in business now for a little over 20 years to reflect on all of my terrible failures during those 20 years. And you know, for the last 5 years, I've been running the data science and big data group at auction.com. A little advert over here. Auction.com, we are the leading online marketplace for real estate. You can go online to our site, buy and sell commercial real estate, residential real estate, anything from a $10,000 Detroit foreclosure through to a $50 million New York office block. You can go and buy and sell those online. The other pitch is we are hiring in Silicon Valley and Irvine. For those of you in the School of Information, we've actually hired people into our UX department, but we're certainly with the data science program interested in talking to people. So if you have a chance afterwards, please, and you're looking for a job, please come and talk to me. Okay, that's the commercial over. Houston, we have a problem. 55% of big data projects fail. We've spent the last day and a half learning about these wonderful models and all the great decisions and the huge dollars that we can do. But the reality is that if any way you look at it, these projects fail at an astoundingly high rate. And given the costs that we've heard associated with them, this is not a good thing. And let's not beat about the bush. This stuff, it's hard. It's really hard. And sometimes it's really hard. And quite frankly, sometimes they go down in flames. And today, I'm going to talk to you about why they go down in flames. And based on my own experience, based on my consulting experience, and based on having talked to colleagues as well. We have 5 reasons. And let's start off with probably the biggest reason for the failure of these projects. First one, we didn't eat our big big project greens. What do I mean by this? So the reason most big data and predictive analytics, data science projects fail is for exactly the same reasons that other large-scale big projects fail across the enterprise. They fail because we didn't get any sponsorship. We didn't get sponsorship even in business, the line, in marketing, within our technology department. They fail for that reason. They fail because we did not have a clear business objective. A clear business objective is not, we're going to move from our enterprise data warehouse to our wonderful Hadoop stack. That is an objective for spending and wasting a large amount of money. They fail for organization and people reasons. If you look at large-scale big data projects, they will typically involve a line function. They may involve marketing. They may involve technology, engineering, operations, the data science team themselves. All of these people have to interact with each other. We have to build or train new skill sets. They fail for organization and people reasons. And they fail for basic project management reasons. We didn't manage scope. We didn't manage risk. We didn't manage timeline. We didn't manage budget. Okay, so make no mistake about it. When you're going into this stuff, these projects are going to fail for exactly the same reasons that every other project failed. Okay, so now let's get on to the stuff that's a little bit more specific to the data project. A couple of conversations, a couple of talks talked about this, but they failed because we didn't ask the right question. What do I mean by we didn't ask the right question? Well, let's have some context. Perhaps one of the most fundamental things I learned at business school was in economics. I think it was 205, microeconomics, taught by Professor Ben Hermelin at the Haas School of Business. And he came up with this line, which is very true. Information is worthless unless it has the power to change a decision. And we've seen various outcomes of that. And let me give you a couple of examples. Those of you who've got spouses will be well aware of this. So I'm driving down the freeway, sitting next to my wife, and all of a sudden we come upon some traffic. And it's traffic, I go, oh, and I turned to her and I said, honey, should I carry on the freeway or should I take the side streets? And she comes back to me and she says, you know, Sheridan, I think at this point in time, the side streets would be better. And I go, I think I'll just carry on the freeway. And so what did I just do that? I asked for a piece of worthless information because it had no power to change the decision that I was going to make. I was going to carry on doing exactly what I was doing. Unless, of course, I was being obtuse and I was just picking the opposite, in which case it would have obviously had an impact. What is the most important question then? And the corollary to information is worthlessness as a prior to decision is, what are the decisions that we are going to change, right? That is the question that we have to ask. And so then, how does that manifest itself in us asking the right question? Well, let's start off from an example from predictive analytics. This is a very common question that people ask. Who here has done problems around customer lifetime value? Anybody? 1, 2, 3, 4, like 20, 30 people. Wrong question, okay? You were asked the wrong question. If you started with that, you were asking the wrong question. What it might be the right question. And why is it the wrong question? Well, in an esoteric way, okay, so we get a number, right? So we find out that our lifetime value is $5, $50, $500, $5,000, whatever it is. But there's no decision connected to that. So a better decision, and there could be many decisions that come up would be, how should I allocate my marketing mix next month? And let's think about that, because if we start from that problem, we think, yes, well, we need to know the lifetime value, but hey, it's also important for us to understand our marketing attribution model, to understand our marketing costs, to understand how things are balanced through that. So you'll see very clearly that the second question on here was tailored around a specific decision that we were going to make. The third point, and this may be, this may be sacrilegious to this audience, but data science has its limits, right? And very frequently, it may not be the right tool or vehicle that we come across. Number one, the absolute most dirty secret in data science and predictive analytics. Nearly all of the work we do is predicated on the fact that the past is a good predictor of the future. Now, often that may be true, but sometimes it's not. I mean, let's take this example. I've given the cumulative revenue curve. We could think of that as a lifetime value curve for an individual user. But hey, new products may be introduced. New business models may come in the future. Our model shifts. And hey, guess what? There may be massive market or regulatory change as well, which pushes us down. And so let me give you an example from my time in a games company. We were trying to calculate, we were looking at the lifetime value. We were making a lot of kind of important marketing mix decisions. And we were on Facebook. And then in January of 2011, an absolute bombshell hit us. We were using our own payment service, cost of 5%. Facebook said, 3 months' time, you must use our service, a cost of 30%. All of a sudden, our margins have been absolutely and fundamentally slashed. Now, there's no amount of work I could have done in any of my predictive analytics, looking at my past set of data to make a case and understand that. And so here you see a clear case of some of the limitations of predictive analytics where we're doing it. And as we're looking at from this cave, you'll forgive this line to remember it, but shifts happen. Sometimes it is okay to use different methods. It's okay to use different methods and tools. Not everything has to be your Hadoop cluster, right? There's plenty of good data science work that gets done in traditional relational databases, whether that be MySQL, Oracle, SQL Server, whatever you want. Heaven forbid, you don't always have to use R or Python, right, to do stuff, right? I've seen good data science work in Excel. Is it scalable? Well, perhaps not, but there are other tools out there. If you guys haven't seen it, go to Google and use their predictive analytics engine. You can go and you can get your predictive analytics up and running and working in a day, right? And when you ask yourself, when you're building that fancy model with all of those things, if you can't do better than Google's model, why are you building it, right? So there's a lot of kind of, we kind of go back into the kind of a lot of fancy new stuff, and sometimes we don't need to. Secondly, crowdsourcing, right? There are wisdom in crowds, right? Some data is not necessarily known. When we're looking at forecasts, and outside, we can use crowdsourcing techniques. We also need to be able to understand that and not take as a fait accompli the data set that we are given. Facebook are the masters of this. You over there, you go there and you're clicking those like buttons and you're thinking, great, I'm giving this got a great like to my friends. What's Facebook doing? That's another signal that you've given to Facebook all over the place. And so you need to think about your data set. You need to be thinking about how do I capture new and different data sets. And some of those data sets, you know, can be crowdsourced and survey-based. It's okay. Scenario analysis. 1950s, right, developed in classical scenario analysis, right? I asked data scientists, how many people are really familiar with classical scenario analysis? Here, we've got probably 5–10% of the audience over here. 1950s, right? A lot of the work of classical scenario analysis was done during the Cold War, you know, and so you'd come out with stuff. But let me give you an example of why kind of traditional statistical method may fail and scenario analysis will give. It's 1955, Cold War, bad state, and we have two outcomes. You know, obviously there might be more, but let's assume there's two outcomes. One is there's a 90% chance that the Soviet Union will not bomb America, and no people will die. There is a 10% chance that the Soviet Union will bomb America and 100 million people will die. So we could run an expected value calculation on that. And the expected number of people to die, anybody? 10 million, right? But what do we know? We know 100% for sure that that scenario is not going to come out. So knowing that number is completely and utterly worthless. Scenario analysis, if you don't know it, spend some time. Game theory, right? We always think, I mean, a lot of our data kind of relies on, you know, what we think we're going to be doing in our curves and stuff. But a lot of modern game theory is a useful technique to understand how and when our competitors are going to react to stuff. And then finally, simple models. I was at a dinner of a lot of data science leaders in the Bay Area a few months back. And a woman who heads up quite a famous company that's pre-IPO, and she heads up the data science division, kind of spoke to the table and she says, you know what the most underused data science technique is? And we all looked at her and said, no. She goes, division. Right, so you know, and of course we all burst out laughing, right? But her point was really, really well taken, right? Is that, you know, she said, you can't have just one number, you got to be able to have at least a ratio. But, you know, often sometimes a ratio between two numbers is good enough to give you some insights. And, yeah, we're spending our time going through logic regression models, random forests, and God knows what else. But sometimes simple models are okay to use. Okay. This one as well, limitation. So it's a classic. People, when I tell people this, they think I'm absolutely insane. We may not want our answers and predictions to be right? It sounds totally and utterly counterproductive. We may not want to be right, but let me give you a classic case where a lot of analysis we do. Revenue predictions, right? We go and we predict a set of revenue and the outcome we predicted 1 or 2 quarters out. And guess what? We hit those perfectly. Well, from a data science perspective, we can go, yay, our model's correct. But from a business standpoint, we never beat par. I had this exact situation in another games company I worked for. We had a beta program. We tested pre-beta. We had lots of games. And what we were able to do is we were very quickly able to tell whether a game would be an A title, a B title, or a C title based on the beta responses we got back. We correlated some metrics to the future projections. And you know what? It continued and continued to be a good predictor. Terrible, terrible outcome for the business. Because what we didn't do is we were not able to change when the product was a B or C product and move it up the ladder. We wanted our predictions to be wrong, right? We wanted to be able to make decisions that proved that our predictions were wrong. Did not happen. We don't understand the statistic, the monster we call statistics. So this as well, and I come from, my background at undergraduate is mathematics and statistics, right? So we've got into a situation where a lot of data scientists come from different backgrounds, and I actually think that's a very good thing. But sometimes we lose fundamentals around statistics. The first is correlation is not causation, right? And okay, so you're saying like, he's written the most blinding statement up there. We've been told this a gazillion times in our undergraduate, in our graduate, in our work. We repeat it like a tantric chant. Correlation is not causation. Correlation is not causation. But when it comes down to it, do we really follow through on this? What happens if you look at enough random data, right? I tell you what, you will find patterns, and it's worse. It is absolutely worse in the big data world because we now have the tools, the power, the technology, the methods to compare 500 variables with 500 other variables, and guess what? We're going to find patterns in those sets of data over there. The most seminal article in data science, in my opinion, was a short one in The Economist 3 months ago. Look it up if you've not seen it. It's called False Hope, and it details this problem in detail, in particular reference to the financial services industry. But the truths kind of apply right across. And let's just give an example over here. So this is divorce rate in Maine and per capita consumption of margarine, right? now perhaps you could come up with a reason why these might be correlated with each other, right? So I struggle, right? Variance kills. So often we'll come up with predictive results, right? So somebody will say, our predictive lifetime value, let's take that again as an example, is $20. But how often do you see the variance, the standard deviation, the range published against that? Very, very rarely. Let me give you an example here, Belgium and Holland. Example, with not real numbers, but we would have this in the games industry. We've got 100 users, 10 of them are paying. We have an average revenue per user in Belgium of $5.80. We have an average revenue per user in Holland of $14.80. Who should we target? You all think you're stepping into a trap, which you are. But if you look at it, the difference between Belgium and Holland is one whale purchase. 100, 1,000. Just one data point changed slightly over there. And all of a sudden, so if we start making decisions based on this, like we're going to run into problems. And it also goes to the fact that perhaps we've not really thought about it. I mean, with Belgium and Holland, I'm European, and forgive me if there are people from Belgium and Holland over here, but demographically, economically, socially, there is not a lot of difference between Belgium and Holland when we chat over there. So why did we make a decision to split them up over here and think about them as two separate groups? And that's something we've always got to be thinking about as we divide and divide data. Not all of us have Facebook where we've got 100 million signals coming in every nanosecond, right? Some of us have smaller samples, and we've got to be able to work and understand the limitations of smaller samples. Speaking of samples, bad samples. This is another thing that just kills you, right? Picking a biased sample. We come through and not understanding how our sample has changed, right? Surveys, classical case where we often end up picking a biased sample. By definition, often in surveys, if they're voluntary, we're picking up a biased sample. Not understanding how your sample changes. Hey, guess what? If you've just marketed to the US and you've got all of your data on your website based on a bunch of US stuff, and you go what? And now you start marketing to Asia, right? And you assume that the US market is all of a sudden the same as the Asian market. Well, that's going to be a really, really bad assumption. So not understanding how our sample and understanding sample I see as a common cause of error and a common way that we screw up. And so what are some of the solutions around this? I think first off, if you've got a data science team, if you're able to have it, have at least one hardcore statistician as part of that group, one who's been through the rigors of statistics. I think it's fantastic that we've got, lots of people from different disciplines in data science, but we can't forget that a lot of it is based on fundamental statistical principles. Out-of-sample tests, right? You should build your model and you should think about doing an out-of-sample test. And most importantly, continuously testing that model, right? So you built that model 1 month, you've assumed your correlations did equal causation, right? Because we've all done that. But then check it the next month, the month after that. Did it drift? Did it follow? Did it continue? Variance and display, we other thing. This is something I get at with all the people who show me analysis, and they show me a number, and I say, well, what's the range? What's the variance? And very rarely has it been in the presentation that I received it. And let's understand the sample and how that changes through. We didn't build the last mile. This is my fifth and final point. And what do I mean by this? For those of you who know and understand the telecoms industry, you'll know the phrase the last mile. And the last mile is basically from the sub-communications box to your home. And it is the most costly, the most expensive, the most difficult to maintain part of that communications network. But it is the most vital, because without that, you, me, this audience, we don't get our communication services. And the same is true in data science. Again, a seminal article, I can't remember where it was, around the last mile being the most important part of data science. So what do I mean by that? Well, the first thing is we come up with the model is great, and then sometimes we come up to now what, right? And what I'd argue to you is that you should build your data science, your predictive analytics, with a product and service mentality, in the same way that other engineering teams, other groups, other product teams within your organization are doing. What might be some examples of this, right? So we think about our predictive analytics as a product or service, not something that we just do one time, but we continuously deliver. We continuously improve on. For us, in auction.com, every predictive model we do that's going to get deployed, we turn into a RESTful API, right? That is our point. That is our point of product. It's not integrated or hard-coded into some system. It's delivered as an API, so we can integrate it internally with into our internal systems, to our website, and to third parties eventually as well. And think about the work you do from a product methodology standpoint, right? Research, the typical things we do in product lifecycle around resource planning, sprints and scrums, tickets, roadmaps, measurement, all of those things that are absolutely essential to keeping this going. Because if you think of these, if you run into the challenge of thinking of these as a project, sooner or, with a clear fixed date when we deliver, sooner or later you're going to run into problems with model drift, with technology change. You've got to be thinking on a continuous basis, and to think in a product and service mentality is absolutely the right way to be thinking about it. So I want to wrap up, and hopefully there'll be a little bit of time for some questions over here. But let me, two points I'll give up for you. Rich Lyons over at the business school once had a line which said, I think on average, if you go for a course at Berkeley, people remember 5 things from it, right? And you list out in one slide the 5 things you were supposed to remember. I'm gonna go for the real high jackpot with this high performing group and hope you can remember 2 from just 30 minutes. But focus on the decisions you want to influence and the outcomes you want to change. And the second one, especially to the technology vendors out there, don't come and crucify me afterwards, but don't get hung up on the technology, models and data itself. There's so much more to this, right? I think back at the technology decisions I've made, and we've made as groups, whether it's R or Python, whether it's Cloudera or Hortonworks, and yeah, we probably made some good decisions and some bad decisions, but I don't think back at any of those decisions as fundamentally costing or failing us the project. And so, as I say to people when we say, well, we've only got $100,000 to spend in our organization, what technology should buy? I say, you know what? Spend it on a good change management consultant, right? So that would probably be money better spent than spending a ton of money on the technology itself. Okay, let's call that a wrap. I've got Q&A. How much time have we got now for Q&A? for about 5 minutes. And then if you don't get to me online, LinkedIn, by all means send me emails, send me messages on LinkedIn over there. Gentleman in the second row.
I just wondered if you could maybe give an example of big data analytics MVPs from like a sprint or scrum cycle.
Yeah, you know, that's an excellent question. So the question over there was, could you give an example from, you know, a minimal viable product? That's what MVP stands for, like of something you did to start in the sprint process. I'll absolutely give you an example there. We were building a recommendation engine. This was about 1.5 years ago, and one of the things I have in my data science and data groups grouping is I don't OK projects that don't have a deliverable in more than 3 months, right? They have to deliver something in 3 months. And so we took, as a base case, this prediction engine. Now we wanted to get this on our website, we wanted to get this into our Salesforce tool, but we took a very narrow view standpoint. We took one line business, our single family business, and we took one application use, which was email. And so we developed a very, very small scope to pressure test our predictive analytic model. And we worked a session of, I can't remember, 4, 5, 6 sprints like this over a quarter to deliver against that. And then, most importantly to the product methodology, to get measurement and feedback to understand how that model was performing, how it was doing, what was the lift in our email response rates as a result of that. And by the way, we used that. That's a great way of going about it, because you also use that to get additional funding and additional sponsorship to move forward with that project. Does that answer the questions?
Yeah, thank you.
Hi, over here. In an organization, what are your thoughts between having a Six Sigma teams for process improvement versus maybe like a data science team? And if an organization is making a decision to go one course versus another?
You know, so the question, if I can paraphrase there, is you know, we've got a Six Sigma team or a data science team. We have to make kind of a choice one way or another and which way to go over there. You know, I'm not sure I can necessarily answer that question definitively. I think, you know, Six Sigma, for those of you who don't know that, is a quality methodology to be able to get down to kind of standard deviation of kind of 3 sigmas each side. And you know, it was pioneered a lot by GE and the Japanese in particular around process improvement. I think, you know, my answer, I'm going to take what the economists would say. The typical answer is it depends, right? I'd say that your biggest chance of success might well be pairing the data science with the Six Sigma team, right? And not trying to make the compromise. If I had my choice between that, it's somewhat of a Hobson's choice, I'd probably say reduce my scope and let's see if we can make a team consisting of data science and kind of Six Sigma black belts together and focus on a smaller scope of work.
Thank you.